So, good afternoon, good morning, good evening. Welcome, everyone. Thank you for joining us for our first webinar in 2018. You're here with the Food Packaging Forum Foundation, and we're very pleased to have Elko Pike, who will speak on prioritization of unknown substance in food contact materials today. So we are recording this webinar, and we'll make it available shortly after the webinar on our website, so you can also access the slides then and listen to the whole webinar again. And unfortunately, we've been forced to limit the participants for today's webinar due to software limitations. So for the future, please register as soon as possible for our webinars so that you make sure you get a spot. And if you can't attend, even though you've registered, then just please let us know so we can give that spot to someone else. Thanks a lot. Okay. A few words about Food Packaging Forum. So we're a charitable foundation established almost 6 years ago in Zurich. We do science communication on chemicals and all types of food contact materials and articles, and we're interested on migration of these chemicals and their impact on health. We focus on the current science, and we have an interdisciplinary perspective. We have various different products. We have a newsletter which is free. It comes out twice a month. You can subscribe to that on our website. We have dossiers, sort of briefing papers, background papers on different topics. We do webinars like this one. We have an annual workshop which is open to anyone to participate, and we also publish peer-reviewed scientific articles. And our work is enabled by donations which are given to us unconditionally, and I would very much like to thank our donors for supporting our independent work. And if you consider our work valuable, then please consider making a donation. How to do that, you can find out on our website. Okay, so what are we going to talk about today? As I mentioned before, we have Elko Nicolas Pike here with us today. Thank you very much, Elko, for joining. You just finished writing up your PhD thesis, and I think you submitted it last week. So
Yep.
I'm very grateful that you are taking the time to share your work with us today. And of course, congratulations on completing your thesis. We will after Elko's talk, we will open up for some questions and discussion. So we'll have about 10 to 15 minutes for that. If you do want to send in questions, or if you have comments to share in the discussion, then please send us an email. I've disabled instant messaging for this meeting. So if you want to get your questions through to us, just send us an email on events@fpforum.org, and we'll make sure to get to as many questions and comments as possible. Okay, and now I'd like to give the floor to our speaker, Elko Pike. Elko has a master's degree in analytical chemistry from the Vrije Universiteit Amsterdam. I probably said that incorrectly. And at the moment, he's working at the Danish Technical University at the National Food Institute there. And he's been working during his thesis there on quantifying, identifying, and prioritizing food contact chemicals in paper and board food packaging. And without further ado, Elko, I would like you to go right ahead. I'm going to upload your slides. And then you can take over the floor, please.
All right. Thank you for the introduction, and good morning, afternoon, evening to everyone. For the next 20 minutes or so, I would like to introduce you a little bit to some of the research we've done in this project, and mostly we've been looking at food contact paper and board materials, and looking at what chemicals are in there, and specifically focusing on those that we haven't seen yet. Let's see if I can switch slides. Yes, we can. So first of all, I will give a very brief introduction into non-intentionally added substances, NIAS, and why these are potentially a problem. Then I will explain what exploration actually means, the way we used it in this project. And then I will go a little bit more into the three parts of exploration that we have used, which is semi-quantification in order to get a concentration estimate, tentative identification to find out what chemicals are there, and finally risk prioritization, which is trying to combine that information in a risk assessment way. So when we look at the assessment of chemicals, and specifically the risk assessment of chemicals, it is mostly a knowledge-based decision, which means that in order for a chemical presence to be properly risk assessed, a lot of knowledge is needed. So you need to know, for example, the amount of chemicals, whether these are intentional or not, the intake routes, and also some compound-specific knowledge like possible toxic effects, what chemical identity does it have, how much are we exposed to. And so the thing is, in order to get a really good assessment, you need to have all those things available. When we look at non-intentionally added substances, we can often see that especially the compound-specific parts are usually unknown or otherwise unavailable. So that means most NIAS are unknown compounds which have no identity, we do not know the toxicity, and we do not know the exposure levels. So that is actually very problematic because that means they cannot be properly risk assessed. And that actually makes NIAS a potential problem because we cannot be certain whether they are a problem or not if we do not have the knowledge. And because safety is a knowledge-based decision, because we do not have a lot of knowledge about NIAS, we cannot ensure safety very easily. The other problem related to NIAS is that there are not tools available to improve the existing knowledge. So in order to actually get more knowledge, we need tools. And the funny thing about that is in order to develop tools that can generate knowledge, you need to have some knowledge. So actually what happens there is it turns a little bit in a circular motion in that you do not have enough knowledge to develop tools, and you do not have the tools to develop the right knowledge. So in essence, you get a little bit deadlocked there, which makes NIAS especially problematic because it's really, really difficult to start tackling the problem. So the difference to what we know and what we need to know is so large that as a matter of fact, bridging this distance is very, very difficult. So how that affects NIAS and its component IAS, which are the known substances, is that in most cases when we are dealing with an intentionally added substance, we are able to do something about it because we have pre-existing knowledge on it. For most NIAS, because there is no pre-existing knowledge, the option is often to do nothing. And this is not a choice, this is something that is imposed upon risk assessors, upon scientists, is because there is such a deficit amount of information, you are forced to do nothing. And it is my strong opinion that if we choose to do nothing about the chemical substance, it should be a deliberate choice and it should not be an imposed choice. So most of the NIAS that we know, but a very larger part of those that we don't know, end up in the do nothing road. In the sense that we cannot do anything about them. Whereas most IAS we have the knowledge for, so we can do something about them. This creates a very funny situation actually, where the IAS and the known IAS are easy to investigate because we already know them. So we get this circular motion that because it's easy to do, we can do it again. So we are always sailing the same ship. And here I'm going to use a ship analogy because it quite well illustrates the problem, is that we have an iceberg of which the majority of the iceberg is underwater. The ship, as I like to call it, which are our current methods, are able to see only a very small portion of it. And they can see it very well. But when we want to look at what's below sea level, we need something different than a ship, which might be a submarine or whatever your creativity allows you to invent. Either way, it needs to be something different than a ship. And that makes them a lot harder to investigate, because obtaining a submarine is a lot more difficult than obtaining a ship, which means that most laboratories, most companies do not have the knowledge, do not have the equipment to look at the unknowns, which are under the sea level of where we normally are looking. So we see there is a lot of research for the bottom of the, for the top of the iceberg, where the IS and the known IS are. And we have a substantial smaller amount of research for the unknown part of this, which is under the sea level, because we don't really have the methods to do so. So that is the problem with NIAS, is that they're below the sea level. Chemical exploration is a tool specifically designed to look at what is below the sea level. So chemical exploration can be quite simply stated as a type of untargeted discovery in complex samples, but also in simpler samples. It is basically a tool that allows the building of knowledge. Whereas most of the targeted methods are focused on a specific compound or a specific compound group. You can think, for example, about highly potent substances like PCBs or PAHs. Most of these are found by targeted methodology, which means we analyze the sample based on what we already know. We expect these compounds to be present there, so let's see how much of that we can find. Whereas the submarine, the untargeted discovery, is focused on building knowledge on substances we might not know that are there. So chemical exploration is very useful in the sense that it's a first step of filling information gaps. Normally, when we are dealing with unknown NIAS specifically, we have to go from having absolutely no data all the way to knowing everything in order to do a risk assessment. What chemical exploration does is it fills that very first step, making it easier to make estimates. And from there on, from the estimates, it should be easier to get the full data, rather than having to make the full jump in the very beginning. So filling information gaps in early stage assessments is one of the key things exploration should be able to do. In that sense, when we're talking about chemical substances coming from food contact materials, we need to know specifically how much is migrating, so how much is in the food. And we also need to know what is migrating. So we need to have some information about the chemical structure. And the eventual thing that we want to do is we want to use that information in order to prioritize which chemical substances in which concentrations are more likely to be riskful than others. So we need to make a distinction in risk between these chemicals. So now that I've explained a little bit what exploration and how NIAS are related to that, I would like to share some of the work we did with exploration, so the methods we developed and how the thoughts behind some of them. So exploration is on its very first nature an unbiased analysis, which means that it should not have a targeted component or as little as possible. So we do not want to know beforehand what we're looking for, because by default we are looking for unknowns or unexpected compounds. The other thing that we did on the side is a wide sweep extraction of the samples, so paper and board samples in this case. You can see on the image on this slide is actually one of the extracts that we prepared from a pizza box. But we also figured that because there are no official migration tests for paper and board, it's usually you do whatever you want or use TNEX. I will not go into details why we didn't choose TNEX. It's described in one of the papers we will publish soon. I'll maybe go into it a little bit. But either way, we did a different type of extraction, which we like to call the total migratable content, which can be easily explained as everything that could migrate, but that does not necessarily migrate under real conditions. So it's a little bit an overestimation, but it's something that's below a total extraction because we're only looking at migrates. So if we want to start exploring this world of chemicals, of NIAS and IAS, everything that we can find in paper and board, one of the first things we want to know is how much is in there. For most of us, this seems like a very illogical step, because usually what you start with is trying to find out what's there. this to us was not really a limitation because we really wanted to decouple the quantitative data from the identity of the chemical substance. So we wanted to develop a way to quantify a chemical substance without necessarily knowing its chemical structure. And that was challenging. For those interested in reading the full technical details, which I will not go into here, I have written down the reference format here so you can look up the paper. I will just describe shortly what we did and how it affects the quantification, but the entire details are in there, and it's heavily on the analytical chemistry. So if you're not very well versed in that, it might be a very difficult read. So what we did basically is we did some type of untargeted quantification, which means that in order to quantify a given analyte, we used a surrogate standard. So we used what we called a marker, which is another chemical substance with a known concentration. And based on optimization of selecting markers and analytes, so making combinations of markers and analytes, we were able to semi-quantify compounds inside the sample without knowing what they were. We did this with a threefold error, which is, by analytical standards, a very large error. So practically, it means that the quantification has a lot of uncertainty. And uncertainty is a word you're going to be hearing coming out of my mouth a lot for the next 10 minutes or so, because that's basically what we did, is uncertainties. But we also realized that when you're dealing with the option of having no data or having uncertain data is definitely preferable. So in semi-quantification, the method we developed was relatively fast in the sense that you could get the information from a single run with a single sample. So that means you didn't have to collect hundreds of standards for all the compounds, but you could actually do it all in one run. We made the method independent on identification. So that means even if you were unable to identify a chemical compound, you could still have concentration estimates. And we made it to work on any detectable compound that we could find in the chromatogram. In this case, we used liquid chromatography with electrospray ionization. So anything that is detectable through there, we were able to quantify. If it doesn't ionize or if it's not visible in a mass spectrometer, then we were not able to quantify simply because we didn't see it. So the disadvantage of working like this is that we have relatively large error margins, which is a little bit a trade-off between being very specific, like most quantification methods, where you use one compound for one standard, which delivers fairly small error margins, but requires a lot of work, a lot of standards, can be very expensive. And the other thing is that this method required dedicated optimization. So that means in order for it to work, you need to optimize the instrument very specifically for this type of work, which can be quite time intensive, to be honest. So on the one hand, we have a method for semi-quantification, which tells us a little bit about how much is there. Then we also want to know what is there, because that is relevant too. So we want to know what chemical structures can we find, and can we relate some of these chemical structures to these concentrations. Again, we recently published a paper on this, actually. It's not officially published yet, but it's available. What we did here is we used the high-resolution part of the time-of-flight mass spectrometer in order to analyze the specific fragments of a chemical compound. Based on those fragments, we tried to correlate these to existing databases of fragments, and we tried to recreate the image of the chemical compound. Again, this is also very, very detailed, so I will really not go into it, but I will explain a little bit what the outcome of it is because we are using a number of databases with chemical compounds. We are reporting the best matching chemical structure from a database on the spectrum. So that is a very important aspect because it means that what we predict as chemical structure is limited to what we are able to find in the database. So it's not an infinite pool of chemical substances we can recreate. We're basically looking to what matches best to what we observe. The advantage of using databases is that these are very easy to generate. The only thing you basically need is a chemical structure. And again, like the semi-quantification, they have independence from reference standards. So if you want to identify the structure of a chemical compound, you do not need the reference standard. If you want to confirm the structure, that's a different thing. So as I said already, the predictions for tentative identification are that you're limited to database scope. So if you have very poor, small databases, it means you're not very likely to get very good matching results. And all of these predictions are in silico. So that means they are computer-based fragmentation comparison. If there is something that we know about these models, is usually they're quite error-prone. Even though they automate a lot of the work and they can give very good results, there is always the probability of outlier, of weird results, which means that these predicted structures do need to be manually checked by a human before we can just go on, because sometimes the predictions can be quite interesting to summarize that. So on the one hand, we have the suggested structures, and on the other hand, we have the semi-quantitative data. And that is the key frame of the exploration. So by using these tentative identification along with the semi-quantification, we now have, from going to having no idea of what's in there to having some idea about the structures, about the quantification. So we know a little bit what is there, and we know a little bit how much is there. Now, this in itself is very interesting information, but it would be more interesting if we can take this a step further and if we can look at how would this look based on possible risk. So which of these substances are more important than others? The first thing to do here is that we have to convert the fact that we have concentrations estimated from an extract to an actual exposure. Because we might know, like, let's see, I think I have a laser dot here. So we might know what's going on inside of the sample, of the sample extract, but that doesn't mean we know what's going on inside food that we're eating. So how much are we actually getting in? In order to convert this quantitative amount to an exposure amount is we made a rough assumption that what is inside this extract is the total migratable content, which is again a term that's coming back, for 1 square decimeter of food contact material. So everything that we can find inside of this sample is everything that can extract from the material into the food under the worst possible case. That means that based on this, the level of substance found inside the extract, we can calculate an intake. And in order to do that, I'm actually not sure if I added, no, I haven't added that slide. We can use the generally accepted EFSA estimate, which states that every person eats 1 kilogram of food in contact with 6 square decimeters of food contact material. And this is related to plastic. So that means if we extrapolate this assumption, we could say that what 1 human eats a day in food has the potential to be in contact with whatever we can find in 6 of these bottles. The real assumption is a little bit more delicate than that, but I haven't added it here. I guess I did it because of the time that I have. So on the other hand, we also need to know something about hazard, because now we have an idea about the concentration, we have a little bit of an idea about the exposure, but we need to know what is the hazard component of a chemical substance. The problem here is that the tentative identification that we are using gives multiple structural suggestions rather than one. So that means for any given chemical we find inside of our sample, we can have up to 5 predicted structures, which may be similar or, as shown here, can actually be slightly different. Now, what we know about slightly different structures is the moment you try to do a literature search on structures that are slightly different, you might find widely differing results, actually. That's because some toxicology studies are done 30, 40 years back. Some of them are done maybe 5 years back. So it's very difficult to compare toxicology data. And it becomes extremely problematic when you have very different structures that have very different literature effects, or some structures just cannot be found in literature. So obviously relying on existing literature data is not very viable for these predicted structures, and generating your own data is not really viable either because you don't really know the structure. So in order to elevate this, we moved into using quantitative structure activity relationships, or QSAR for short. So we used QSAR models to predict some of the most common researched negative outcomes of chemicals, which is carcinogenicity, mutagenicity, and developmental toxicity. So we use the chemical structures on these compounds, and we input them into a QSAR model, which gives us a prediction about the possible effects this compound can have. So now we want to move a little bit closer to an application of risk. And one of the conclusions is that calculating a true risk, like risk assessment does, is not really possible with this approximated data. But that doesn't mean it's not useful, because we can still get some kind of perception of risk, as we like to call it, by combining this estimated hazard, which is a component from the QSAR, and the predicted structure. And we can use the estimated exposure, which is a combination of the quantity from semi-quantification and the identity, to determine something like a risk likeliness. This is not necessarily a risk assessment per se, but it gives us some idea of having a compound with certain hazards at certain levels can tell us something about a possible risk. This is the part of the study that we're actually still working on. So we haven't published it yet. I will be happy to do it soon. But basically what we decided to do here is based on this input information, the chemical structure, the predicted hazards, and the estimated exposure. We used a combination of human-based expertise, so these are risk assessors, and we use rule-based decisions to classify the compound into what we like to call high or low risk. So, I mean, rule-based decisions are fairly simple. For example, is the exposure above a certain level, or are there QSAR hazards that indicate carcinogenicity? And human expert decisions are a lot more subtle in the sense that they require an evaluation of the full data. So a human can much easier decide whether a compound is acceptable or not, whereas a computer doesn't really have the capacity to do that just yet. So we used the exploration data, so the semi-quantitative data and attentive identity, and we used an expert assessment, which is the thing I just showed. So it's a rule-based decision combined with an expertise decision, so a risk assessor. And based on that, we classified the compounds into three main groups. The first group is the simplest, which is saying that you do not have enough information to classify a compound. That means for some cases you did not get a quantification, or you did not get a structure, or the data has so much uncertainties you cannot move forward. So in those cases you cannot really give a good decisive information. So usually the advice for those compounds is to reanalyze. The other two groups, they are a little bit more implicative in the sense that we can say, okay, some of these compounds, they are of lesser concern. So, for example, we are finding a polyethylene glycol, or we are finding a straight alkane in very low concentrations. These are usually compounds that do not really have a high chance of risk, in the sense that if the concentration is low and if there are no hazards associated, the probability of risk is fairly low. And the other group is the compounds that we do expect are of concern. So these can be compounds, for example, that are carcinogenic, or compounds that have very, very high concentrations, which can lead to high exposure. And by subdividing these compounds in these main groups, we can create a preliminary risk ranking of compounds that we expect to be of high importance to risk assessment, and compounds that we expect to be of low importance to risk assessment. And by subdividing the chemicals in this way, and by having the exploration data, we can prioritize substances for risk assessment. So we can say that if we find some likely carcinogenic compound inside of the extract, that's obviously something to look at. Whereas if we find very unlikely risk substances, you could say, okay, these probably should not have the priority because the priority should be spent on alpha and beta, which are more dangerous compounds. So coming back to what exploration and in turn prioritization is, it's also important what it is not. So for instance, it is not a replacement for risk assessment. So what I've shown so far is not meant to replace risk assessment or to avoid it. It is just a way of prioritizing substances before risk assessment. It is also not a complete representative chemical image of food or food contact materials. As I said, you are always limited in the sense that some analytical methods are limited or some data is not collected. So the image we have is informative, but it is not complete. It is also not intended to replace hazard or exposure assessments, because the assessments that I've shown have significant uncertainty, and even though the same could be said for some of the hazard exposure assessments done today, the ones we have here have really, really large uncertainty. So they do not replace assessments or migration testing. They are simply a way to see what's in there without having to move towards these highly complex assessments that require detailed information. So summarize what exploration and prioritization is not. It is not a definitive answer to this quite difficult problem. But I do like to think it is a step in the right way of trying to comprehend this problem and trying to visualize it. So then we can move also to what it is, which is maybe even more important, is exploration and prioritization is a way to provide early stage knowledge on undiscovered chemicals. And this is probably a very important feat because NIAs are difficult to trace down because of their knowledge deficiency, as I've stated at the start. So breaking the cycle by inputting new knowledge is very valuable because it means the talk can get going about chemicals again because we have some information. Even though it doesn't contain uncertainties, it does get the flow going again. As I've shown in this presentation, as we probably will show soon in the article, is you can obtain preliminary assessments for possible hazards and exposure. And based on these, you can identify possible risk from these poorly studied substances or unexpected chemicals. By using these preliminary assessments, we can have some kind of idea of risk. So exploration and prioritization is very strongly a strategy to help knowledge building. And by doing that, it also aids risk assessment by providing a way to prioritize chemical compounds based on the assessments that we made on this knowledge building. So it has two very important components, of which one is having more knowledge or creating knowledge, and the other one is prioritizing the chemical compounds based on what we have seen. So it is not a definitive answer, but it's definitely a step in the right way of trying to understand and visualize the problem. So I've spoken a little bit about vicious circles in my presentation, and now we have arrived at the end of my presentation, and I would like to make another circle. I have shown you this intersection of choice early in the slides, and I would just like to repeat it that if we decide to do nothing about a chemical problem or a chemical substance, it should be a deliberate choice. It should not be a choice out of incompetence or inability to do anything about it. If we do nothing, it should be a choice that we make coherently and responsibly. And if we do something, the exact same is true. But it should not be a matter of doing nothing because we can't do anything, because we don't have the tools, we don't have the knowledge, because that is the situation we're at now, and that is problematic, possibly, especially for NIAS. So the key message at this intersection of choice that if we're gonna do nothing, it should be a well-considered choice, and it should not be something that is imposed upon us. So with that being said, I have arrived at the end of my presentation. So thank you for your attention, and thank you for the collaborators on this project. Also, it's the Friends Agency for Food and Safety, especially on the risk assessment part, and of course the various people within DTU. So thank you.
Thank you so much, Elko. This is one of the downsides of webinars, that you don't get a round of applause, which you would have earned. Thank you for this very, very clear presentation. Great. So I would like to open the floor for questions. Do we have any questions? Okay, I've got a few questions. So first of all, you mentioned databases that you use to compare structures. And I was wondering, can you tell us a little bit more about these databases? Did you self-compile these? Are they commercially available? Are they free databases? What's the deal with the databases?
Yeah, so I can tell you that. So it's in the paper, but I would be happy to recite it. So the databases we have are mostly publicly available. They are composed, for example, one of the REACH annexes is one of the databases on the compounds possibly of risk. Another one is ChemSpider, actually. So that's a very large database. It's an online database. Basically, we use two types of databases: specific ones and non-specific ones. So the specific ones are useful for finding known structures like PEGs, like printing inks, and the unspecific databases are very useful for finding chemicals that you do not know to be present. So basically, you can input any database you like. And right now I used 5 databases, 3 specific and 2 non-specific. And of course, ideally, these databases could be made available from the producers of paper and board, because then you actually have a good database.
Mm-hmm. Are you, just to follow up to that, are you working with paper and board packaging producers on something like that? Could that be?
No, but I have given at several presentations, I have given them the message to start sharing the data, because most of the times they're not willing to share it because they're afraid of breaching some intellectual property or whatever. But these databases are so simple that the only thing you need is a chemical structure to build them. And that makes them extremely suitable for this, because I mean, a chemical structure itself is unlikely to be proprietary.
Mm-hmm. Okay, thanks, Elko. Good. Then just maybe a general question. You mentioned at the beginning, when you do your non-targeted analysis, that you're dealing with about a threefold level of uncertainty. Is there a general trend as to in which direction this uncertainty goes? Are you generally overestimating concentrations of the substances, or are you generally underestimating concentrations, or is there no such general trend you can say for this method?
That is actually a good question. As far as I know, and I cannot say this with absolute certainty, it goes both ways. So it's not necessarily an under or an overestimation. It can shoot both ways. I think the trend is to have more overestimations than underestimations, but I don't know that from the top of my head, to be honest.
Okay.
But the threefold error is just something that's inherent to the untargeted work, because there have been publications that showed fourfold errors as well. So it's around that range right now, and it's definitely something that needs to be improved, but something that we didn't really have time to dig into very much deeper.
Okay, thanks. Another question from one of the participants. Can you estimate how many substances in percent are not detected at all? So again, with this threefold level of uncertainty, can you estimate sort of a detection limit that you have for this method?
Oh, that's a good question. The detection limit is fairly low, fairly good actually, in the sense because we use time of flight, so that means we are able to go pretty low in most cases.
Can you say what low means in your world? Are
I
we
would
talking
have to.
PPT, PPB,
It's
PPM?
probably PPB level,
Okay,
PPB,
thanks.
PPM between there. I think we've
Okay,
gone down to the PPB level. I think it's well possible, but
okay.
we haven't validated the method for its sensitivity. We mostly validated it for its use to detect unknowns.
Mm.
So. But there's another part of that question is as well as how many compounds are you missing, which is a question related to we use LCMS. Of course, I'm missing a lot of compounds you would normally see in GCMS, and I'm also missing the compounds you would see with other types of ionization. So right now, what we have is although it's a very large number of compounds, it is only a fraction of what's in there.
Um, can you comment on the main differences between your method, your approach, and previously published other non-targeted screening methods? For example, using bioassays.
The bioassay approach is one that's very interesting. Actually, I think the main difference here is that we start with the quantification. So we start based on exposure-based assessment, to say so, and then we start looking if these exposures have some sort of hazard associated with them. Whereas with the bioassay, I think you're working more from seeing if there's a hazard and then trying to identify which substances caused the hazard. I think both methods have merit. The advantage of the method we used here is that it can be used to obtain a lot of chemical knowledge on a sample.
Okay. So, and maybe just a last question. So there's a new method under development using thin layer chromatography. Are you familiar with that method? So combination of thin layer chromatography with non-targeted um, uh, analytical chemistry and sort of the interface between the two, the separation and the analytical chemistry work is that the thin layer plates are treated with a bioassay, kind of reported
Okay,
gene
no,
assay.
I
And
haven't heard of that.
no, okay, good. Well
But
then,
sounds fascinating, actually.
yeah, I think so too. Okay, we've got one more question. Um, Given that there is no specific EU legislation on paper and board, and given that other non-harmonized materials like lacquers and so on are used, how complete do you consider your database for intentionally added substances for chemicals in paper and board?
That is a good question. So, I mean, if we look at some of the databases we used, they have maybe 5,000 compounds in them. And then if you look at the Swiss database for printing inks, it has 5,000 compounds in them, which is only a part of the total. So actually, the question there is, I think the databases we have now are fairly limited in that respect and will definitely need some sort of expansion. Then again, you could also ask, I mean, they are IAS, but they're quite unwanted in the sense, so they should be included. So the current databases we use are not extremely comprehensive. We have mostly used them as a proof of concept in this case, and it would definitely be very useful to expand these. And that is also part of the message that basically I've sent to industry. I doubt they recognized it. Is that having these databases will improve these methods and will improve the ability to target NIAS as well.
Yeah. And it would help everyone really. So maybe that's something we should look into, how to get collaboration on that. Thanks. Very last question. What would you like to see for your strategy, exploration, and prioritization in relation to the food packaging market? What's your wish or dream with all the knowledge that you have built? Good question.
Is it an analytical dream or is it a
You can answer that as a scientist or as a citizen. I leave it up to you.
So I'm just going to answer it from my analytical side here. I think what would be very, very valuable is improving unknown identification. So the ability to identify an unknown compound, currently it's extremely convoluted. It takes a lot of time and resources. And I think, and it would be great if we could automate a lot of this process by using machine learning, actually. I think it has a lot of potential in using machine learning algorithms to predict chemical structures based on mass spectrometry data or NMR data. At the moment, it's mostly manual labor, and that manual labor is expensive and not very fun when you're dealing with 5,000 compounds.
Yeah.
Um,
Okay, great. Well, Elko, I would really like to thank you very much for your very clear presentation. I learned a lot from you today. And before I let you go, just to highlight, we're doing a webinar on the 27th of March. We have Christina Nerin, Professor Christina Nerin of University of Zaragoza, who has agreed to do a webinar. She's just published an article together with several co-authors on migration of a substance that is reprotoxic from multi-layer plastic materials. So you can check the FPF news today if you want to read more about that. And there's a link to the original article there. Then also please save the date in your calendars for our annual workshop, which will be held on the 4th of October in Zurich. And we will be talking about similar to what Elko presented now, predicting and ensuring the safety of food contact articles, science trends, and digital opportunities, which maybe could be machine learning for improving the identification of unknown substances. And with that, I would like to thank everyone for joining us today, and I wish you a great day, good night, and hope to see you soon. Take care. Thank you.
Thank you.